Welcome everyone for this session called Pimp My Trace. My name is Henrik, and as you can see in the title, we're going to talk about traces, of course. So who am I? Let me introduce myself. My name is Henrik. I'm a cloud native advocate working at Dynatrace a bit more than 4 years and a half almost. And otherwise, I'm a CNCF ambassador since more than a year. So pretty much involving in the open source space. I'm trying to be involved in this amazing cloud native ecosystem community and observability community. So I love to be working with this community. But prior to this, I was a performance engineer. So I spent all my career as a performance tester or performance optimizer. I don't know how you can name it, but yeah, testing, breaking, tuning, optimizing systems. I think it's an amazing practice to start learning very quickly all the architecture pattern that you may have in the industry because you're touching base so much of those different architecture types. So that's why performance engineer is still in my heart. You will see that there will be a pinch of performance stuff here in this presentation. So I'm when I have time now, it's getting less often than it was in the past to produce some content on a YouTube channel called Perf Bytes. So it's the red icon that you can see in this slide here with the QR code next to it. So if you are up into the performance engineering world, check it out. We provide some methodology content about performance engineering. And then 4 years ago, when I started my adventure in the observability space after a long career in performance, I started another YouTube channel called Is It Observable? Dedicated to observability, open telemetry, Kubernetes, security, you name it. So check it out. The QR code is also there. So what are we going to talk about in the next couple of minutes? Well, a couple of things. Yeah, you, as you expect, probably sampling, tracing, couple of things. So we will remind a couple of things about sampling, the importance of sampling. I think sampling is a topic that is often not probably understood by our users and our community. I think it makes sense to remind these aspects. We're going to also mention about the reality of distributed tracing. Even if we have an open standard, there's a reality behind the scenes. We need to understand that reality to handle probably the challenges. And then, of course, we'll cover the sampling decisions that are available in the Open Telemetry project, head sampling, and of course, the one that are in the collector. So we'll see the distinguish. And I will, of course, give my recommendation on which one should be better. And then recently, the committee has worked on an improvement. You will see why it makes sense that improvements comes into the game. It's called consistent probabilistic sampling. So we'll explain what it is, what it brings for us. And last, of course, we'll look at best practices in terms of collector deployments when you have to deal with sampling. And last, of course, is benchmarking. Yeah, benchmarking results depending on the settings that you may use in your collector. All right, let's start. So today, we can technically say that we are pretty cool kids. You know, we have open telemetry, we have a standard. We use everything as code. So we use a lot of GitHub's workflow, and we made a commit, we make a PR, we accept it, it goes in production. We have automatically dashboards. We have instrumentation. So we get everything, and we create SLO, and yeah. I mean, compared to the past, we are pretty cool kids, but wait a minute. Maybe we should check our engine. We need maybe to understand what's behind this engine, because being a cool kid is great, but not understanding what type of car we're driving on how it works doesn't really make sense. All right, so let's go back. So our engine. Yes, our engine we're going to rely pretty much on tracing. You have metrics and logs, but here we focus on tracing. And the engine for this is tracing. And as you know, I mean, no surprise with distributed tracing, a trace is made of spans. So you have a different layer of spans. And of course, if you have a high number of layers of spans, it makes it the transaction may be complex. So the depth. And then, of course, on the root span, you can get the overall duration of the transaction. So that's very good, pretty much good information. And then within the transaction, if one of the steps is failing, Yeah, everything was failing. So we can track also the potential errors, the exceptions that happens in our code, and that is just fantastic. And as you know, all those observability solutions out there, they get those OpenTelemetry traces, and they extrapolate some stats. So failure rates, response times, throughput. You can get the endpoints out of it, get some statistics about the endpoints. And from there, we saw great, so that we take those informations, if we don't have the metric, and we start to build dashboard or SLO and everything, and report that to those systems. So, all right. So, but question is, why do we have sample? I mean, what's the purpose of sampling? So let's explain this briefly. Well, sampling is a bit like this example, which is a running race. Let's say we're organizing a small running race in a village. We have about 10 to 15 runners. And we ask Kate and Mike to track the timestamps. So every time there's a runner going through, Kate is positioned in one stage of the race and Mike another stage. And then every time the runner comes through Kate, she's taking the timestamps of the runner, noting down into a piece of paper or an Excel sheet, whatever you prefer. And then Mike does the same thing. And at the end, with all the statistics, they could basically get some details about how fast is the runner, the pace between two stages. So pretty much interesting. And then that keeping everything into records makes pretty sense with 15, a very low number of runners. And now the reality. We have a marathon. We probably have 30K plus runners running in the city. So Kate and Mike, again, they've been organizing small events. They go in this big London marathon, for example, and Kate is positioned on one stage and Mike again. And then here they clearly realize that it's impossible to keep track on all those data. It's impossible to record it at the right pace. So Kate makes the natural decision. So, on my stage, I will take 30% of the runners. Okay. And Mike says, in my stage, I will take 20% of the runners. So we may say, okay, with those statistics, we could assume that's going to be the minimum of both, which is 20%. But that is completely wrong. It's basically statistics. It means it's going to be 30% multiplied by 20%. And at the end here, with the stats that the data that Kate and Mike has collected with the sampled data, they are only focused on 6% of the runners, which is pretty low. So if they keep track on, I don't know, someone who is has an injury, then we will consider that record. Or if it's a professional, we will take that. So at the end, it's not really representing the average runner in any case. It's very difficult, and we don't keep track on all those different details. And in case of distributed tracing, it's exactly the same thing. You have different layers, different microservices. And then on every single microservices, it could happen that one component decide to sample, and then later on, another component decide to sample in a different way. And then we push all those spans to a collector, and then we distribute it to our backend. And then, as you saw, we take advantage of that data. So here, we're looking at the failure rates, the response times. But if we take the same example, we are technically looking at an average of 6%. So it's an average of average. So I clearly have no idea what that really represents. And the big problem, you will see that currently in the OpenTelemetry specifications, in the trace context that we are passing to share the trace ID, the span ID and everything, we don't store the sampling decision. So when those data comes into any observability solution of the market, we have no idea of what we're dealing with, how much data we're using, and how it's been sampled across the architecture. So that's a real problem. So how can we basically face it? So first, let's understand the actual reality on how our systems has been utilized and how we could basically improve the sampling decisions. So the reality is that we have different endpoints in our systems, different microservices, and every endpoint is not equal. I mean, if I take a microservices, let's say here we take an example of a /product, a product product catalog component. And the product catalog component has different endpoints or services, gRPC services, that is exposed across the different microservice architecture we have. So you could have /order, /product, placing an order, the /health. And as you can see, every endpoint is not utilized the same way. The /product is used way much often, /health as well. And /place and /place order is obviously used less often because it's related to the actual application, the conversion rate, and so on. But still, I probably want to have more samples of placeholder compared to the others because basically it could be impacting our business. So applying a fixed sampling rate across a component is the current way of doing it, but it doesn't really make sense. If I apply 20%, then I will have 20% less, less chance to get a placeholder transaction into the overall traffic that goes to that component. So that's the first piece. And there are a few property agents that has this dimension into consideration, so they don't apply the right things. But here we're focusing mainly on the collector. So how can we basically, if we know that this is a challenge, so how can we basically resolve that? Well, few things. Here, what we can do is utilize a component, in fact, a connector in our OpenTelemetry collector. And that connector is called span metrics. And the purpose of that connector is very simple. You send your spans, it goes through that connector. So the connector becomes like a sort of an exporter. And then once it goes through that component, it translates those spans into metrics and then push that to a metric pipeline. And then we can basically utilize that metrics as a traditional metric that we have produced. So why do we want to do this? Well, because before you actually sample, you take 100% of your traffic and you go through the span connectors, and that will get you basically all. You don't lose any details. You get response times, the number of requests, their status, the endpoints, basically everything. So what we want to do is every trace that comes in, we convert into metrics, and then once it's been converted, let's figure out how we want to sample that. All right, and at the end, with the data coming from span metrics, we could basically have the number of spans per seconds per workload, so we can find exactly the right throughput that is coming in. We can keep track on the response time, split it by the endpoints, the URLs. We can look at the error rates, exactly what we had initially, just based on traces. Same thing, but here we know that it's a time series. We know that we have everything, and we are not losing any details. So now we've converted into metrics. Now let's focus on the sampling. So how do we do that? Well, let's focus on the two approach. We mentioned that we have in the OpenTelemetry project, we have different way of doing it. We have the head sampling and then the one that provided by the collector. So starting with the bad. Sorry to say that, but it's going to be the head sampling. Well, head sampling is great in a sense where we have a component, and then from the component level, say we're going to apply a sampling decision directly here. And the only problem with the current state is that the head sampling is very basic. We have a couple of options: always on, like a switch, 100%; always off, we turn off the switch, 0%. Then we have parent-based. Parent-based, we'll see, we'll touch base on this. Really interesting, could make sense. Especially if in a microservice architecture, we have dependencies and everything. And then as we have trace ID ratio, and you will see trace ID ratio is the exact example that we had with Katie Mike. So let's start with the parent-based. Parent-based, well, it makes sense if we only focus on transactions that belongs to, spans that belongs to an end-to-end transaction. Let's say here, I want to have the checkout transactions or a payment. Then if I put payment and checkout, I configure them as parent-based, they will only push their spans if they are actually involved in a transaction. So here in that case, the root of the caller is front end. So every time front end starts the trace, goes to checkout, and then checkout says, "Oh, I'm part of the transaction. I'm going to send my trace." So perfect. So then you only focus on dependencies. Perfect. But there's a few limitations. The first one is, if you have any health check, and then sometimes those health check could fail, then you don't have any traces. So no way of understanding why those failing. That's one is disadvantage. The second one is asynchronous processes. If you have any task that runs on parallel, do anything like this, they are not part of any transaction because they are asynchronous. So you're basically losing also those details. So not perfect for everyone, but still it gives an answer. Then you have the other one, trace ID ratio. Here the game is at each individual component will define a ratio. So here I want to have 25% on the front end. I want to have 10% on the catalog. I want to have 10% on the card, and so on and so forth. So here you're basically sometimes, and that's the problem, it's a pure guess. You put your fingers in the sky, say, oh, please give me the numbers for the front end, and boom, we have the numbers. So like I said before, the only problem with this approach is that when front ends start to sample, checkout doesn't know what was the actual ratio that front end decided to put. So there's the different ratio applied are not connected to each other, so it's completely disconnected. So that's not consistent. And at the end, let's say that I'm focused on having an end-to-end trace to the payment because it's critical for my business. Then here, if I take that example, it's going to be 25% multiplied by 10% multiplied by 10%. And at the end of the day, out of 100% of requests, I will have only 0.25% with an actual end-to-end trace. So pretty low. And again, I have no control on if it's a slow transaction, if an error. So I'm looking at something, I have no idea what it actually represents. So it's basically could be very risky to take to make analytics and conclusion based on that. So that's why the Observability project decided to improve it, and there is a new way, a new sampler out there called consistent probabilistic sampling. So that's a big name, a lot of math, but what does it mean? Well, let's take back to the example of the race. So we have Kate, we have Mike, and here Kate and Mike, now instead of doing pretty much a random decision on how they're going to sample, they say, okay, the runner has a bid on when they're and then we are going to apply a decision based on the bid number. Everything which is under 200 will be 20%, and so on and so forth. So at the end, Kate decided to make 30% here on the bid number, and then Mike 20%. And here, compared to the previous example, we are actually getting the mean between 30 and 20% because we have a reference number that is based, so we can control basically how we sample. And at the end, we get bigger, at least, numbers of samples to make actual decisions, which is better than what we had before. And in the case of Trace ID, in the case of distributed tracing, the bid number, yeah, we don't have any bid on our distributed traces, but we have a trace ID. And here is an example of a small trace ID. And every transaction goes in my systems, they have their bid number. So which means I will rely on the trace ID to make these decisions. So better sampling decisions applied across the architecture. And the other big advantage of it is that of providing this new way of doing things, it's also because you're making a reference of a bid number, so we need to store it somewhere to cross that hash map, or here it's a hash map, but to cross that that reference number that will be used across the architecture. And that's why they have improved the trace context. So here we have the trace context, here we have the trace parent, and that's what, in the top, this is what we actually get. So trace parent, 0, 0 means is it being sampled or not, and then here it's the actual trace ID, and then we have the span ID. So at the end, with these details was very limited. Are we sample or not? That's it. Now it adds a new element in the trace context, which is the trace state. We have UT corresponding for the sampling decision. So TH, it's a bit difficult numbers, but TH give you the actual sampling decisions that has been applied, and RV is the actual hash map. So it's not the trace, it's the trace ID that has been serialized. So it's basically easier to store and share it across the trace context. And at the end, with the TH number and the actual RV, we can basically retro-engineered on what sampling decision was applied at one level of the transactions. Because here you can see 1 minus sampling ratio multiplied by 2 exponential to 56 gives you the actual the TH number. So this is how we can basically recalculate how the sampling decision defined. So it's just a math or equations, and then you get it. So meaning that every backend of the industry now can figure out who has samples and how it has samples at one stage of the architecture. All right, now after covering the improvements on head sampling, let's cover what we have in the collector. So we have two ways. So the first one is the probabilistic sampling, and the second one is tail sampling. You will see. So probabilistic sampling is an amazing. It's better than head sampling, but still, I would say that I have preferences. I will tell you in a few seconds which one it is. But the probabilistic sampling is amazing. It doesn't sample only traces. It can sample logs. That's the major advantage compared to the other ones. And it has three modes: hash seed, proportional, and equalization. So hash seed is basically mainly designed for logs, where you can have a reference of a field, and you'll do that. The sampling seed would be based on that hash seed. And then we have proportional equalizations. So they are basically designed for traces that has been pre-sampled with head sampling. And again, that means also that it's been using consistent sampling, because otherwise you don't have the details on what was actually sampled at that moment, and so on and so forth. So if so proportional will be set to equal to set an equal ratio. So say I want to have 50%, and then he will apply 50% across all the components, all the spans. Equalization here, the probabilistic sampler will calculate the actual ratio to apply to have an equal consistent sample. Let's say my target is at 20%, apply whatever you want across the spans, so then we get 20%. Then we have the big one, sample like a pro, which is tail sampling. So tail sampling, how it works? Well, simple. We send 100% of the traffic to our collector, and the collector, we will create some rules based on different things. We'll touch base on those in a few seconds, meaning that the collector, before it actually makes a decision, will store every spans in memory until it gets the actual trace, end-to-end trace. And once he has the end-to-end trace, he will look at the rules that we've defined and say, okay, should I sample or not? So what are the rules that we can define? And this is what I love about it. You can do rules about many different areas. We can look at, I want to look at specific attributes that is in our spans. Let's say we put a spans that don't sample, so then whatever happens, those spans will never be sampled. So the end-to-end trace will never be sampled. So if one of the spans has that attribute, then the entire trace won't be sampled. Then we have, let's say, by response times. My response time needs to be take 100%. Take everything from the moment the transaction is above 1 second and above 5 seconds and 10 seconds. And then, so you can put a min and max. Of course, you can just put a min if you want. But at the end, you can focus on transactions that are slow. Then we can all do the same thing. Say, whatever happens, if there's an error, take it. I want to have the errors. Then you can also have the options to rate limit. If something is very chatty, you can say, this endpoint is giving me a lot too much noise, so I'm going to apply by default these sample decisions. And then you can also add a probabilistic sampler, say based on conditions. If this is coming from that services, because we know it's very chatty, we're going to apply 1% or 10% or so on and so forth. So you have the actual control. And those rules are ends, so if one rule match, then it will be applied. So you can basically say, I want to have the errors, I want to have the slow transactions, I want to have the priority ones. You can be very smart. And at the end, the overall data that you get back in your systems, you will get, that you will have the errors. You will have the slow transactions. That you have the priorities. So at the end, you're looking at something that could be used as a diagnostic tools. And when using this, because you're using this caching approach or storing in memory, you can expect to have increase of memory. So that's why there is a lot of tuning about sending a timeout. How long should I wait until applying the decisions? So if you have a transaction that takes 20 seconds, maybe you should wait 20 seconds. If also the numbers of traces that you want to store in memory. So that also is important to fine tune depending on your collector. Also, there is a cache size. So depending on how much you want to sample or not sample, you should increase both one or the others because it will be stored in memory. So doing this is great. And because it's going to consume more memory, then you suddenly want to start load balance your traces. Yes, you can do that. It makes sense. So for that, this is what I recommend. You have one collector deployed as a gateway, for example, and this collector will be responsible of enrichment. So enriching your traces with extra metadata. You can also take advantage of that moment to start producing your span connector metrics. So then you have the full data, and then you use the load balancer exporter. And the load balancer exporter is smart because you could make it the reference of a field. So here in our case, trace ID, and basically all the trace ID, all the spans belonging to a specific trace will always go to the same collector, because at the end, remember, the sampling decisions stores all the spans in memory and then makes the decision. So you may want to make sure that all your spans of a given trace goes all the way to the same replica. Otherwise, yeah, it doesn't make sense at all. So also, the other thing that is really important is that there's a feature flag where you need to enable the extra metrics that the collector can produce. So you should enable this to get extra details. So let's take a look at the benchmark. So I did a lot of tests. So I've updated the test 2 days ago. So this is what I've done a few months ago, and I saw some weird memory behavior. So I dropped the policy 2, policy 3, policy 4. I focus on 4 policies, 5 policies, and 6 policies, and then adding this configuration of caching. And every of those collectors basically says I have 4 policies, so errors and slow transactions and priority flags and probabilistic samplings. And then I did the same thing with different priority flags. So playing on the HTTP error code, for example, of a gRPC, playing on the HTTP response codes of a gRPC and so on. So basically it's the same one. I would do a test during 1 or 2 hours, measure the footprint, and then I show the results. So let's check out the results. So if you want to replay those results, here's the QR code to the actual repo. Check it out. There's all the instructions. So basically, I have two applications, some load tests, and of course, different collectors. So one collector, like I said, do the enrichments, the metrics generations, and then the other one for sampling. So let's look at the results. So the purple bar here is because I did some mistake. I had to restart. So don't consider the purple bar. But at the end, what we can see here, so the adding extra policies is putting very limited differences in some of the resources. Few megs, few millicores difference between one and the other. So the number of rules will have a small increase, but it's not gonna be significant. So you don't be worried about that. Your collector can take a lot of rules, so it's not about the complexity of the rules. It's going to be more about the volumes that you will face it. And then I was looking at the other angles. What is if I add the caching layers, would that provide me a way of controlling the resources? And the responses is yes. Here you can see that I'm saving 25 millicore by adding the caching layer, and the other one I'm saving about 80 megs of memory. All right, the takeaway I would say, use parent-based. If you really want to use head sampling, use parent-based. Be cautious about trace-to ratio because it's just, you don't know what, you don't have no control. If you have the options to use the consistent probabilistic samplings available in Go and Java, do it. That's great. Otherwise, do tail sampling. Define precise sampling rules. Enable collector metrics to see your sampling decisions. Use several collectors. Doesn't make sense to have one collectors, and take advantage of the load balancer exporter. I have a lot of videos out there about sampling and other stuff on the YouTube channel. Check it out. It's out there. It's free. If you love it, love it. If you hate it, yeah, hate it, but let me know. So then I have a feedback and I can improve the channel. All right. If you have any questions, I would be very eager to answer all your questions.